So welcome everyone. Today I want to give a combinatorial interpretation for the Jack polynomials. So remember we defined Jack polynomials via this by this inner product. So we define this inner product on the power sum symmetric functions, where we have the usual z lambda and we have this extra parameter alpha raised to the length of lambda. And we said that with our proof that the Jack symmetric functions p lambda alpha are characterized by the same kind of properties that Schur functions are with respect to this inner product. So they are orthogonal with respect to this inner product and have are expressed in terms of monomials, in terms of partitions which are less in dominance order. So I want to, so I didn't say much about them, but I want to give a nice combinatorial interpretation.
What about P alpha with itself, the inner product?
Sorry?
What about what about P alpha with itself, the inner product?
This one, right? P lambda alpha, this one?
Yeah, P lambda, P lambda, that's what I mean.
Oh, yeah. So there's no, I mean, it's non-zero.
Okay, but for that you don't.
It's not orthonormal.
Okay.
Yeah.
But we also don't. Do we know some nice?
Yeah, we do. We do know some nice formula.
Okay.
So, right. Okay. So let me give a combinatorial formula. Oops, sorry. So combinatorial formula. It's a bit involved, so please bear with me. But please do ask questions if anything is not clear. So P lambda alpha. So I will use notation from the last time where we defined this notation. So remember that we have semi-standard tableau of shape lambda, and lambda I of t is the subpartition of lambda formed by entries less than or equal to I in t. And then we know by the semi-standardness that the cells of lambda I minus lambda I minus 1 are in different columns. So that much notation I will reuse. And now let me define some standard notation, standard quantities for a partition. So, for a suppose. So if you have a partition lambda and a cell C in lambda, by which I mean a cell in its Young diagram. So let's say something like this, and I have this cell C. Then so A of C, which is the same as a lambda of C, which is okay. So C is ij. So it has row index I and column index j. So this is lambda I minus j. This is the arm length. So let me say what that is. So you look in the same row to the right, and that is A of C. And L of C, which is again L lambda of C. This is lambda prime j minus I. This is the leg length. And just to clarify, let me finish this. This thing is L of C. And just to clarify, neither the arm nor the length includes the cell itself. So A of C plus L of C plus 1 is the famous hook length. Underline all these. Okay. Now here is a complicated function. So define B lambda alpha of C. So alpha is our parameter for our jack, lambda is the partition, C is the cell. This is alpha times A lambda of C plus L lambda of C plus 1 divided by alpha A lambda of C plus L lambda of C plus alpha. Okay, so the only difference between the numerator and the denominator is this factor of, is the last term. So let T lambda mu is the set of, be the set of semi-standard tableau of shape lambda and weight mu. That is to say, the contents are given by the partition mu. And remember, if that happens, then mu is less than or equal to lambda in dominance order. Okay. And this curly C of Ti. Okay, this is a bit complicated, so I'll give an example in a second. So these are the cells of lambda I of t. These are, remember, all the cells in all the cells in lambda which are less than or equal to I in the tableau T. In rows which belong to the cells of lambda I t minus lambda I minus 1 of t. Minus the same thing where you replace rows by columns. Okay, so it's a bit hairy, so let me give you an example. It's 4, 3, 3, 2, 1. Please bear with my drawing skills. So here is, let's say I. These three cells contain I. Okay. And so now I have to look at all the cells which contain, all the cells in the rows which contain I. So these, the row 1, 3, and 4. And I have to look at all the columns which contain I. So all the columns in lambda which contain I. So these are columns 2, 3, and 4. And if you do the subtraction, the 3 cells that do belong are here, because they are in the rows but not in the columns. These cells are in the rows but also in the columns, so they go away. So only these 3 cells belong. So this is whatever.
I have one question.
Yes.
So here the case is quite simpler, but it may happen that there could be some conflict, like one might not be a subset of the other. So how
No, it's a set difference. It's a set difference.
Oh, okay.
Okay, so that's not clear. This is a set difference. I'm not saying one is contained in the other. Here also one is not contained in the other, if you look. Okay. All right. Okay, so here's the theorem. I don't know who this is due to. I'm following Mcdonald's book. So, so the notation, I'm using is this u lambda mu alpha. Okay, so that's the coefficient of p lambda in mu, p lambda alpha in mu. So u lambda alpha, u lambda mu alpha is the sum over all semi-standard tableau of shape lambda and weight mu, the product I greater than equal to 1, and then the product over cells in this set CTI over here of okay, it's really a horrible formula. B lambda I minus 1 alpha of C divided by B lambda I alpha of C. Okay, so it looks quite complicated. So let me show you with an example. So I'll do the same example as for all little work.
Sorry, Arun, what is the left side?
Left side, this is the coefficient of mu in P lambda alpha. Okay, that's this thing. P lambda alpha is when you expand in m in the m's has an expansion like this.
Thank you.
And this is a coefficient, and P lambda, this u lambda lambda is 1. That
So you don't need the mu on the right there. In your theorem.
Thank you. This is a pure number. Okay, it's a rational function in alpha. Okay, so here's an example.
Can you just show the formula for a second? I just want
Yeah.
to copy it.
Yeah, sorry. Yeah. Okay, so let's take again lambda is to 1. So there are only 2 partitions which are smaller than this in dominance order. It's not saying much, there are only 3 partitions of size 3. But these are the 2. So for mu equals to 1, so A, let's take a tableau of the form 1, 1, 2. So 1 comes 2 times and 2 comes once. So this means that lambda 0 is phi, lambda 1 is all cells containing 1, and lambda 2 is 2, 1. And in both, each of these cases, the set, this set C is empty. So it's the empty product. So the set C, and so this means that U lambda alpha is 1, as it should be, because this is the characterization I just said. Right? So if lambda equals mu, you should get 1. And this, if you sort of stare at the definitions a little bit, you will see this. Okay, so let's do the non-trivial example. Okay, so hold on to your seatbelts. So mu is 1, 1, 1. Now there are 2 tableaus, so we need to sum over both. So let's do both of them separately. Okay, so here lambda naught is empty, lambda 1 is 1, lambda 2 is the partition 2, and lambda 3 is the partition 2. So here, as usual, C is empty, but here C is the cell 1, 1. Because, let me show you here. So here is 2. So, so we have to look at all the cells in the rows containing the 2. So that's the entire partition. And we have to subtract all the cells from the columns containing the 2. And that's this cell. So it takes off this cell. So we are left with the cell 1 with coordinates 1. Okay. So for that, let us compute this ratio. So there's only one cell. So let me compute this ratio. So what am I doing? So I'm computing the ratio B alpha for the partition singleton 1, that's the upstairs, for the cell 1, 1. And what is it? So let's go back to the B formula. So it says alpha times the arm length plus length plus 1 divided by alpha times arm length plus the length plus alpha. Okay, so what does it say? So so we are looking at this cell in the partition 1. So there's only one cell C, and that's the entire partition. So the arm length is 0. So alpha times 0 plus leg length, which is 0, plus 1 divided by alpha times 0 plus 0 plus alpha, which is 1 by alpha. And B alpha partition 2 cell 1, 1.
Hang on.
Yes.
Sorry, you lost me at arm length is 0. Why is arm length 0 for that one thing?
No, because the arm length is everything except that cell, no, on the right hand side. So, yes, it is so arm length is everything on the right over here of that cell, but there's nothing on that side more. Okay.
But the thing you were taking was 1, 2, right? I mean,
no. Okay, let's go back. So we are taking the partition 1, the cell 1, 1. So this dummy sort of trivial example. Okay.
Could we go back and just look at the formula once again, Arun?
This one?
Aha, okay. Okay.
So you have
thanks. Lambda I minus 1. Yeah, that's.
you have to take both.
Okay,
so
thanks.
Yeah, so it's really a complicated formula here, but it's nice to see that the answer works in the end very nicely. Okay, so now B2, the partition 2, 1, 1 is this cell in this partition. Now the arm length is 1, leg length is still 0. So alpha, the only thing that changes is this 0 becomes a 1 plus 0 plus 1 divided by alpha times 1 plus 0 plus alpha. So what is that? That is alpha plus 1 divided by 2 alpha. And so my coefficient is the ratio of this. For this tableau is the ratio of these two, this divided by this. So that is 2 by 1 plus alpha, or alpha plus 1. Okay, so I have occupied a lot of space. So let me move this over here. And let's do this. Oops, let's do the same kind of computation here. So by the way, this another check over here is that this C is that. Okay. Again, lambda naught is 5, lambda 1 is 1. Now lambda 2 is 1, 1. And lambda 3 is 2, 1 as usual. So here too, this set C is empty. Here too, the set C is empty. Here it's non-trivial. So let me show you over here. Actually, I don't have to show you. I can look here. So we are looking at all the cells containing in the rows containing 3 minus all the cells in the columns containing 3. And so that's again the singleton cell over here. So it's the same cell C. I mean, there's only one cell, which is the same one as the previous example. But now the partitions are different. Okay, so now this B alpha, the partition I'm supposed to take is 1, 1, and the cell is also 1, 1. Okay, so this is a bit confusing. Okay, and so this is now, I'm running out of space. Okay, let me put it over here. This is that cell, okay? And now the arm length is 0, leg length is 1. So alpha times 0 plus 1 divided by alpha times 0 plus 1 plus alpha, which is whatever it is, 2 by 1 plus alpha. And B alpha 2, 1 of the same cell 1, 1 is, okay, see? So now the both the arm length and leg length are 1. So alpha times 1 plus 1 plus 1 divided by alpha times 1 plus 1 plus alpha. That is alpha plus 2 by 1 plus 2 alpha. And now so the coefficient here is the ratio of these two things. This divided by this. So it's 2 times 1 plus 2 alpha divided by 1 plus alpha, 2 plus alpha. And if you sum the two, we get, so you notice that 1 plus alpha is common, and but when you add the two, that will actually cancel, and you will get 6 by 2 plus alpha. Okay, so it's an easy thing to do, and let me show you on Sage. So I define these symmetric functions. Remember, I told you we cannot use alpha, we have to use the variable t.
Sorry. Can I ask you, why did you add?
That's the formula. We have to sum over all tableau of the same shape.
All right.
So that's why it's a non-trivial. Here, there's only one tableau with that content. Yeah. So I defined the Jack polynomial. So this is what I covered. I showed you last time. And now, if I look at the expansion of the transition matrix of partitions of size 3, you get 1 and 6 by alpha plus 2. This is exactly this. Okay. So when I was doing this computation, I was sure that I've done some mistake, but because there are too many factors, but somehow most of them cancel. Anyway, so this. Okay, so this was.
So this reduces to the shore function expansion at alpha equal 1?
At alpha equal to 1, yes, it should.
Okay.
Yes, well, okay, right. So when alpha equal to 1, the numerator equals denominator, so you get 1 per term.
Okay, great. Thank you.
Yeah. So it works nicely. Oh, by the way, I should say there has been a power cut here. I don't know for how long. So if, I mean, we are running on UPS in my office, so I don't know how long this will last, but hopefully it lasts the rest of half an hour more. Okay. So now, now Mcdonald. So to contrast with Raghavan's lectures and maybe even Radhika's lectures, for me the symmetric Mcdonald polynomials are more natural and somewhat nicer objects. So as usual, these are kind of not motivated very strongly when you see them this way, but hopefully this will contrast with Raghavan's and now Vishwanath's lectures, and it should hopefully complement them. So these are a two-parameter, as Amri mentioned, these are two-parameter generalization of sure functions. And he has shown several special cases, so I don't want to get into that. So let us take the field to be a fraction field over two parameters q and t. So rational functions. Q and t, and define z lambda qt to be z lambda, our usual factor, times this product, which I goes from 1 to the length of lambda. Remember, length of lambda is the number of non-zero parts in lambda. It's 1 minus q to the lambda I divided by 1 minus t to the lambda I. And the inner product, the Mcdonald inner product, if you like, where you posit that p lambda p mu in with parameters q and t is delta lambda mu z lambda qt. So if you compare with the Hall-Littlewood case, we only had the denominator 1 minus t to the lambda I. And so what Mcdonald did was to add 1 minus q to the lambda I to the numerator. And why is this a good thing to do? To see that, I think, okay, so the first thing is a generalization of the Cauchy identity. So I need some notation for that. So recall the Q-Pochhammer symbol. So A semicolon Q subscript n. This is the product I equals 0 to n. Sorry, that's an I. I equals 0 to n minus 1. 1 minus AQ to the I. And the infinite generalization, AQ infinity, this is product I equals 0 to infinity of the same thing. So this occurs naturally in many contexts. So for example, QQ infinity is the Euler product. So this is I equals 1 to infinity, 1 minus q to the I. And this is up to some factor of q to the 1 to the 24th. This is also the eta function in number theory. Okay, so why is this a natural thing to do? In some sense, is given by this theorem. So before that, define. So I'm using the same notation as for the Hall-Littlewood. So capital Pi xy qt semicolon qt. So let x x1 x2 and y, which is y1 y2 etc., be two families of indeterminates. So define this to be equal to the product ij going from 1 to infinity of the ratio of these two Pochhammer symbols t xi yj semicolon q infinity divided by xi yj q infinity. Okay, so the ratio, the difference between the numerator and the denominator is only this factor of t, but of course that changes a lot of things. And so the theorem is that if you sum over all partitions P of the power sums in these two variables, P lambda of x, P lambda of y, divided by Z lambda qt. Okay, so just this was, if q is 0, this is exactly this kind of sum we saw for the Hall Littlewoods. This is equal to this capital pi xy. Okay, so I don't know, but my guess is that this is how Mcdonald sees this as a, or saw this as a natural kind of generalization of the Hall Littlewood case, and that's why it made sense to put a Q over here. Okay. So again, the proof strategy is similar. To the Hall Littlewood case. So you take the log of the right hand side, expand it, and then extract the coefficients. You'll see. Okay. And the next theorem is again a generalization of.
And get the. This is the exact same thing.
Yeah, exactly the same thing. So the right hand side is also a nice product. So this generalizes Cauchy in a very nice way.
Two parameters. Thanks.
Yeah. Okay. So the next theorem is about the relationship between the inner product and this this guy, and it's what essentially. I mean, this is what Amritanshu proved in the case Q equal to T, which is the sure function case. So let U lambda and V lambda be F bases of lambda n F. Remember, F is our fraction field indexed by partitions of n. Then U lambda V mu is delta lambda mu. So these are dual bases for all lambda mu. If and only if sigma lambda U lambda of x, P lambda of y is this product pi xy. Okay, so again, proof strategy is similar to the sure case. Okay, so this seems to say things are.
In U lambda, V lambda also Q and T will be involved, right? Yeah.
Sorry, I can't hear you.
In U lambda and V lambda, Q and T will be involved, right, in summation?
Yes, I mean U lambda, V lambda Implicit, yeah, they have Q and T inside. I mean, they are F bases. So they do have, I mean, oh, sorry. You mean for this, did you mean that? Yeah.
No, I mean that in this summation that here that you have written only X is indeterminate. So Q and T.
Sorry, what? I'm not following the question. I mean, Q and T are implicitly present in U lambda and V lambda.
Q and T are in the ground field. So X, Y are the indeterminates and Q and T are in the ground field.
Yeah.
Okay.
I mean, this condition, if you're thinking of proving it this way, I mean, this condition implies that U lambda and U and V have Q and T in them.
Okay.
Right?
Uh,
Okay. So,
Sorry, when you say Q equals to T is sure, but sure doesn't have any of these Q or T, right? So
yeah, because they'll cancel.
but
Like in the Z lambda, they cancel completely.
Z lambda is pure number.
Sorry, Z lambda QT, they cancel Q equals T.
Yeah, because of this ratio. If you want,
Nice.
take Q equals T equals 1.
okay.
Or 0. I mean, you're thinking of it as a limit, but you know, yeah, you can take some fixed value.
What about the right side though? That is pi. If I put Q equals T, what happens?
So this product will just be a shifted version of this product, and it's going to infinity. There'll be cancellation. So you'll just get 1 by 1 minus xi by j. All the other higher terms will cancel by telescope.
Okay, thanks. Yeah.
Okay, very good. So now I should look at the time. Okay, so let me just, okay, maybe I shouldn't do that. Okay, so maybe I'll go to the construction. So my aim today is to at least state and possibly prove the existence of the Mcdonald polynomials. Okay, so I want to avoid all digressions. There are lots of beautiful formulas, but for lack of time, I want to get directly to the heart of the matter. So what we are going to do now is to define operators which we will construct as for which the Mcdonald polynomials will be the eigenfunctions. So, but of course, there'll be a lot of properties of the operators that will be needed, but you know, we won't have time to go into all of it, but I'll try to illustrate with example. Okay, so we'll define some operators. Okay, so the first operator we need is for U in the ground field. Define the shift operator. So this is T U xi of f at x1 up to xn. This is f of x1 up to xi minus 1. So it just multiplies xi by u xi plus 1 up to xn. This is for all f, or for any f in the polynomial ring. It's not necessarily symmetrical, because anyway this will ruin symmetry. Okay, so this is the first operator, and so the main operator from which things will be constructed is this fellow. So let capital X be another independent indeterminate, dn of x qt be 1 by a delta of x. This is the van der Waals sum over permutations in Sn.
Do you think Arvind's internet is frozen? I can't see anything. Can anyone else?
Same here. Same here. I was wondering whether it was
Maybe
my
it's that
problem.
power cut.
Right.
I will call him now.
Ah, fine.
Hello?
Arvind is back.
Can you hear me?
Now we can, yes.
Yeah, okay.
Yes.
Sorry. Zoom kicked me out suddenly. Yeah. Okay, so let me start sharing again. Okay. So I was defining these operators dn's. Maybe I'll shift all of this. So it's built up of these shift operators. Okay, so I should say I'm acting on lambda n of f. So that is in n variables. Okay, so we will take the limit at an appropriate point. So what we are doing is taking this signed sum over all these shift operators, and we are multiplying by x because we want to extract coefficients of x at a later point of time. Okay, so where remember delta is the staircase in -1 up to 0 partition. Okay, so
So for now, again, a delta x means a delta xn, x1, x2, xn, and then x to the sigma.
yeah,
Okay, thanks.
yeah. So this is the van der Waals. Yeah, is the product.
Right.
Yeah. So then what we want to do is extract coefficients of powers of x. So
There is an x somewhere after the sign too, right? The capital, that's the capital X.
No, that's
this one,
no for that.
This
The
one?
one, no, the one ahead of the sign, that means x1 raised per something, x2 raised per something, does it?
this one, yeah, exactly. So it's a it's a monomial where the first index is the power of x1, second is the power of x2.
I guess there is a small x and a big X. That's maybe confusing.
Yeah, small x stands for x1 up to x. Okay. So here's this is a complicated operator, but we are going to be interested in its expansion in terms of x. So dnx qt is the sum over r equals 0 to n. The product can, there can be at most n powers of x. So this is dnr x power r. Okay, I'll not write. This depends on q and t. X power r. Okay, so we expand this in x and we look at it as operators. So then it's first note that dn0 is the identity operator. It's just one because there is multiplication by one. It's extracting no powers, and this signed sum is precisely a delta. So that
What is
Okay,
dn raised
so-
to the power r?
No, this is notation. This is the rth. This is the rth operator.
Oh,
So
You can put parentheses around the R if you want.
yeah, if you want. Well, we'll mostly be interested with r equals 1, but okay, if you want. So notice that each of these preserves symmetry in the x's.
Can I make a remark about this operator? This is equal in the context of Raghavan's talk. This is equal to the product j going from 1 to n of 1 plus yi capital X. 1 plus yj capital X.
So okay, so maybe I should write that. So from Raghavan's talk. Thank you. Yes. So yeah, please do make such comments. Not take talk. Dn is equal to product j equals 1 to n 1 plus
yj capital X.
This one? Okay.
That's right.
Okay.
So
Thanks.
when you write it this way, then you see that this dnr is the elementary symmetric function in the y's.
Yes, I was going to show. I'm going to do the computation for dn1. Yes.
Yeah.
Okay. Thanks. So example, dn1. So if you take dn1, you will pick only in one term. You will pick the x, and everywhere else you'll pick the 1. So dn1 is the sum over I equals 1 to n ai x t tq xi, where ai xt, this is a short computation, is the product of j not equal to I txi minus xj divided by xi minus xj. So short computation. Okay, so right. So, but I'm a bit confused. So, how do you see this as an elementary symmetric function? Arun? Oh, just you mean expand this out? You're muted. Arun, you're muted.
Yeah, dnr is the coefficient of x to the r.
Right.
But the coefficient of x to the r in this product is yes, that product is an elementary symmetric function in y1 up to yn.
Oh, this is in y1 up to yn. So this your dn1 your.
No, just go to the. You wrote this formula dn equals product j equal 1 to n.
Yeah.
Now, if you take the coefficient of x to the r in that expansion,
sure.
then you get elementary, and the yi's are these difference operators which Raghavan had introduced.
So dn1 is well, of course, elementary symmetric function in the yi's, not written this way.
That's right.
Yeah. Okay, thanks. All right. Okay. So now some properties of dn's. So okay. So okay. So maybe I'll. So one can show the following. Maybe I'll write it as a proposition. Suppose you act the dn on m lambda. This is small x, that's capital X. Then you get a sum over derangements of lambda, that is, these derangements are permutations without fixed points, for those who don't know. Product I equals 1 to n, 1 plus x t to the n minus 1, q to the alpha I, acting on S alpha of x. Alpha is a derangement, so this is up to sine some a sure function for some mu less than lambda. Okay, and so this is a fairly involved computation, so I'm not going to do it. But this shows how the dn's act on the n's and gives you an expansion in the shores. But we know since
Sorry,
the expansion.
Since you say derangements, what if if lambda 1, lambda 2 are all equal?
Right. So I mean derangement.
Think of it as lambda 1 through lambda n. Sorry,
Yes.
sorry.
Right. Yeah. But you know, maybe this is a bit. Yeah. No. It's okay. Yeah. Okay. So since the expansion of S lambda in n mu's is upper unitriangular with respect to the dominance order. So with respect to any basis compatible with the dominance order. So when I expand the right hand side, this already contains sure functions which are less than lambda in dominance order. So when you expand in terms of n's, you will continue to have that property. And so we have the following. Expansion. So dn x q t in terms of m lambda. This is the sum over mu less than or equal to lambda, a lambda mu x q t m mu. Where by looking at this property, you can see that you are only going to get polynomials with integer coefficients as in the expansion. So where a lambda mu belong to z x xqt and a lambda lambda xqt is as a product expansion. So I equals 1 to n, 1 plus x t to the n minus I q to the lambda. Okay, so the diagonal coefficients are nice, but in general, you are always going to get polynomials with integer coefficients. Another property which is somewhat long to prove is that these dn's are self-adjoint. DNRs. i.e. for FG for any f and g in lambda and f, DNR, DNRF inner product G QT is F DNR G QT. Okay, so they have this expansion. Okay. Okay, so but there is a certain problem with these operators. Unfortunately, DNRs do not have the same stability property that I mentioned earlier. Not have this the stability. In other words, if I restrict, I mean, if I take xn to 0, so if I take the homomorphism from lambda n to lambda n minus 1 by setting xn to 0, the DNRs do not go to dn minus 1 R's. That is a problem. But for r equals 1, this can be fixed by defining these new operators ENs to be 1 by t to the n dn1, which I showed you explicitly, minus sum I equals 1 to n t to the minus I. So if you like, I'll put t to the minus n. So this is just some multiplication term. So all it does is it takes care of this problem with stability. Okay. So then one can show that ENs satisfy the stability property and we let E be the limiting operator. So this acts on infinitely many variables. Okay, so now I can state the main theorem. So notice that E's continue to be self-adjoint. So we don't lose that property because this is just scalar multiplication. This extra bit is just scalar. Okay. So here is Mcdonald's existence theorem. Well, existence and uniqueness theorem. For each lambda in P, there exists a unique symmetric function P lambda, which is P lambda x cube T in lambda f, such that the two properties hold. P lambda is the sum over mu less than equal to lambda, u lambda mu, and mu. U lambda mu's belong to F, and u lambda lambda is 1. And the inner product of P lambda P mu, the Qt inner product is 0 if lambda. And Okay, so I wanted to prove this theorem, but I think I'm out of time. But the main idea is to, I mean, it's not a complicated proof, is to show, so main idea is to construct the lambdas as eigenfunctions of the operator. Okay. Now, if I have time, I could have. Yeah, maybe I shouldn't. But I wanted to show you on Sage how to define these. So now you have to take symmetric functions with respect to this fraction field in Q and T, and you again define all these guys. The P's are defined as sim.mcdonald.p, and you can basis expand in the S's, and you get again this upper triangular property. Okay, there are some more things I was going to do, but I can show you how, if you want to work with specific values of Q and T, you can do it like so. So, for example, I define P0T as Q equal to 0. So then I get these symmetric functions with Q equal to 0, Sage knows. And if I expand those in terms of T, in terms of Schur's, I will get this for size 3, and for comparison, if you look at the Hall Littlewoods, it's the same. So you can automatically get all the known guys inside Mcdonald. So PTT is with Q equals 1. So I haven't defined these variables. We can do that. And then if I expand them in Schur's, I get the identity matrix, which means they're Schur's. And of course, you can go ahead. Okay, so I think this is a good time to stop.
So Arvind, can you share the Sage files? Maybe just send them by email or something.
Okay, I have been posting them on CoCalc, but if you want, I can send them. I asked Venkatesh to actually post them all on the website. So Venkatesh, can you take them from CoCalc and post them? I already.
Yeah, I still haven't done. I will do it.
Okay, so you'll find it on the website. Amri's lecture worksheet is already there.
Yeah, yours are not there. Okay. Thanks.
But they're all shared on CoCalc, as I said on the first day. I'm uploading everything to CoCalc where you can play with it and download it.
Yeah, I can't get it from CoCalc for some reason. So anyway, I'll take it from the website. Thanks.
Yeah. So for the last lecture, I plan to give some. So somehow the theme of my lectures has become monomial expansions for combinatorial interpretations for monomial expansions of all these symmetric functions. So the last lecture, I want to give some more combinatorial interpretations which come from things like asymmetric exclusion process, things like that, which are sort of useful and topics of current research. Yeah, okay, so thanks.
Any more questions or comments?
So I want to